Hello everyone, my name is Jayant Nair. I'm a consultant with Wood, and I'm here to present about the topic severe slugging control using deep reinforcement learning, which I'll refer to as DRL going forward, on behalf of my co-authors and colleagues Shirley and Yue. Severe slugging is an important phenomenon in oil and gas pipeline and riser systems, which consist of large alternating fluctuations of oil and gas production. It is a safety and environmental risk and has effects on equipment integrity and well productivity. The figure on the right shows the steps involved in severe slugging. Injecting gas at the base of a riser is a very common mitigation method used in the field, and it is often referred to as riser-base gas lift. The graph on the right shows pressure fluctuations at the riser base. A very high amplitude is a result of severe slugging. Injecting gas reduces this amplitude. However, there is an optimum rate or velocity of gas lift injection. Very high gas lift rates can actually negatively impact well productivity. Severe slugging control, therefore, is complicated. It depends on various factors such as fluid properties, system geometries, flowing conditions, etc. A human operator can only keep track of a few of these at a time. This study is a proof of concept for using deep reinforcement learning to mitigate severe slugging in either open loop or closed loop control. With DRL, however, there are some challenges. The first involves programming the algorithms used typically in DRL. Instead of doing that ourselves, we used a commercially available industrial DRL platform. The second is to create an environment for a DRL agent to investigate and learn from. The physical process of severe slugging had to be converted into a simulation environment. And for this study, the Fabre et al. 1998 model, which is a seminal severe slugging study, was used. This was used in the form of a data-driven simulator. This environment returns states and rewards to the deep reinforcement learning agent, which then decides what action to take. In this problem, the states are the flowing conditions such as pressure, velocities, and fluid properties such as densities. And the action is the gas lift velocity that the agent chooses. The last and perhaps biggest challenge is crafting proper reward functions to ensure the agent is rewarded for taking appropriate actions. These reward functions should not be sparse. For the study, the chosen algorithm was proximal policy optimization, or PPO. Sample reward functions are shown to the right. At the top right, you have a reward function which incentivizes reduction in pressure fluctuations. On the bottom right, there are two reward functions, one which incentivizes low gas lift usage and another which incentivizes high gas lift usage. The latter is only used for edge cases which need a very large amount of gas. Each training episode started with random initial conditions, that is, random velocities, system dimensions, and fluid properties. The training was done for approximately 3 million iterations. The final trained agent performs very well in a benchmark assessment with 50 cases which are prone to severe slugging. In the bottom histogram, we can see that the agent reduced severe slugging in more than 90% of the cases. In the top histogram, it shows that in most cases, the gas lift velocity is low, but in cases which need more gas, the agent chose an appropriate gas lift velocity. This study is by no means complete. There are a few next steps we have outlined. These involve using simulators which can scale to larger system dimensions and capture more complicated multi-phase flow behavior. Another remedial action that is used to mitigate severe slugging is topsides choking. Using such multiple remedial actions as options to a DRL agent will be a very interesting area of study. As mentioned earlier, this is a proof of concept level work, which provides some promising results as we continue to explore the applications of deep learning and DRL specifically to oil and gas systems. Thank you.